one. Roll it. Class is in session, everyone. Today we're going to be doing a little factoring quadratic equations. Now I know what you're saying. Haven't we talked about this before? Yes, we've talked about this before. I'm just trying to get the ball rolling in order to make sure everyone's comfortable with the platforms. Okay? So the first thing we're going to do is do now. And the do now is this. If I gave you something like this, right? It's in standard form. Why is it in standard form? It's in standard form because it's set equal to 0. And we got our quadratic, our linear, and our constant term. So what you're doing is you're factoring the constant, which in this case is negative 14, and it's got a sum to the linear term, which in this case is 5. What are the factors? And again, I'll send you an online calculator to make sure you're good with the calculations, but any calculator will do with these particular problems because we're not graphing, right? So we're looking to factor negative 14, and we're going to add it to positive 5, right? So I say, off the top of my head, well, I know 7 and 2 are a good combination to use because 7 times 2 is 14. And I can get that some relationship depending on which term is negative and which term is positive. I can get that to add or sum to positive 5. Considering I want a positive 5, that means the 2 has to be negative, right? So you're going to say 7 times negative 2 is negative 14. 7 plus negative 2 is positive 5, right? Let me put this down. So what we do, oh, I thought I had that'll do. So what we do is after we do that in the table format, you don't leave your answer in that fashion. You want to put your factors of x squared, which is x times x, and then the work that we just looked at, we said it's positive 7, negative 2, right? Now, we want to go a step further because we want to solve for the roots, right? We want to solve for the roots. The roots are what? The roots are where the quadratic crosses the x-axis. I'm not going to get into that now. In order to solve for the roots, you set this, what's inside the parentheses equal to 0. And this is just a one-step equation. Let me get the water out of the way. And the one step is isolating the variable. So our answer, well, it's a quadratic, so there's 2 answers, right? That's where we get the squared. If the quadratic, the first term is squared, it's a quadratic. That means you have 2 values for x, and these are the 2 values, right? X is negative 7. X is positive 2. And if you look at the relationship between what we solve for the roots and the factors, the roots are the opposite of the factors. Positive 7 for a factor, negative 7 for a root. Negative 2 for a factor, positive 2 for a root. Okay? So that's what we're going to be talking about a little bit today. Any questions? No, I'm just kidding. We're going to do a Zoom little meeting later. If anybody wants to join, that's fine. If you're busy with other stuff, that's okay too. Again, I wanted to have this to be something that we could have some success with and not stress people out. Follow me over here. Because this is a stressful time for people, and we don't need to make it worse than it needs to be. I was all done with my my lessons for the year anyway, and we were going to start reviewing. So this is a good thing to start with because I know we've had success with this. Special case for a quadratic would be this, right? How's this different from the previous example? there's no linear term. We got the quadratic term and we got the constant. If there's no linear term present, that means that the linear term is equal to 0. Very good. So what we're going to do here is we're going to factor and sum, right? We said that the linear term was 0. There's our 0. We said that the constant is -9. There's our -9. You know, you can meander around the factors later, but in order to expedite the process, I know that +3 times -3 is -9. I also know that 3 plus -3 is 0. These are my factors. Roots are the opposite. Right? Shouldn't be too bad. Okay? I think I gave you like, I don't know, 12 problems like this. Again, you have 48 hours to turn it in. That shouldn't be an issue. Let me see if I can get it to it. Okay, let's talk about one more special type of factoring. Right? Now, we have a coefficient that's larger than 1 in front of the quadratic term. That's a special case. When you have a coefficient larger than 1 in front of the quadratic, that means you have to take the GCF. GCF, right? However, I'm looking at this. Doesn't seem like there's going to be any GCF that is going to be able to be used for 4 and 25, right? The factors of 4 are 2. Well, 2 is not going into 25. And the factors of 4 are 4. 4 is not divided into 25 either. So this is not something that's going to be a typical GCF problem. This is going to be something called the difference of perfect squares. Difference of perfect squares. Difference means subtraction. So you gotta have a negative sign in there somewhere, right? Difference. Perfect square numbers, numbers that multiply by themselves to give you a product. That product is the perfect square. So for instance, 2 times 2, this is a perfect square. 6 times 6, this is a perfect square, right? So 2 numbers multiplied by each other or themselves will result in a perfect square product, okay? Very nice. So we know that the perfect square of 4 is 2. We know that the perfect square of 25 is 5. I'm going to put my x. I got to have a negative and I got to have a positive because we know that there's no linear term here, right? The linear term is 0. Okay? So the linear term is 0. That means it does not have a value. That means we have to have alternating signs, negative and positive. If I want to check this work, I can box method. Right? Box method it, make sure that I'm accurate. And I'm going to start with the same quadratic that I began with. Okay? That should have been a positive. It doesn't matter where the negative and positive is. You're multiplying. So 6 and 1, a half dozen, and the other means the same thing. Okay? So you got this, and then you got this, right? When you combine like terms, the x terms cancel out, right? That's where you get your 0, or your linear term equals 0. Quadratic term comes down, constant comes down, and then you get exactly what you started with. So therefore, you know that this is the answer. If I wanted to, not if I wanted to, you have to do this. We're going back to the factors. I'm going to set them equal to 0. And we're going to find out what the roots are. And the roots are going to be this. There's a couple of extra steps here, but not many, right? So you're going to have 2x equals 5, 2x equals negative 5, divide by 2, x equals 5 over 2, and x equals negative 5 over 2. They are the roots, meaning that they would cross the x-axis at 2.5 and negative 2.5, right? If you were looking at the graph. All right, let me see what else. That's been taken care of. I wanted to give you as much information as I can. Let's do a GCF problem so I can show you everything. Again, that was a difference of perfect squares problem, okay, which you will see and you will need to understand when I give you the work. GCF, 6x squared plus 18x plus 12. Okay, good. So this isn't a difference of perfect squares because we have a linear term. In the past example, the linear term was 0, so that was an indication of a difference of perfect squares. That was one indication. The other indication was that we had two perfect square numbers, 4 and 25. These terms here, right? 6x squared, well, the coefficient 6, that is not a perfect square number. 18x, 18, not a perfect square. 12, not a perfect square. So therefore, we need to take the GCF. 9 times out of 10, the GCF is going to be what the coefficient of the quadratic term is. In this case, it's 6. Divide everything by 6, right? And you get x squared plus 3x plus 2 equals 0. And now this is a quadratic where you can use your factor and sum technique, which in this case is going to be 2 and 3, right? We're factoring the constant and we're summing to the linear. The factors of 2, well, it's a prime number, meaning they only have one set of factors, which is 2 and 1, right? If you add 2 and 1, you get 3. So that checks off both boxes, right? The constant, the linear, they both work out. You put it inside parentheses, right? And then you solve for the root, okay? And this is your answer. X equals negative 2, x equals negative 1. So that is a perfect square problem, right? Excuse me. Look at this. This is going to be your assessment criteria that I'm going to post also. Keep this in mind when you're working with the problems. What was the GCF? What factoring method could we use once the GCF was factored out, right? Once the GCF is factored out in this one, we're using factor and sum, right? We're not using difference of perfect squares. But sometimes you may need to use difference of perfect squares after you take the GCF. You'll come across those issues, and hopefully you'll be able to address those when you see them. How can we apply that factoring method? Are your answers clear? That kind of thing. Very straightforward stuff. How many minutes are we up to right now? On the
14.
14 minutes. Let's do one more problem. I know you guys like looking at me.
Mm-hmm.
And I can't say I blame you much.
Mm-hmm.
All right. So hold on a second. Do one more. Oh, that's a good one. Let's do this one. 2x to the third power plus 8x to the second power plus 6x equals 0. Now this is a special type, right? And that's great because that's our aim, right? Hold on. That's our aim. Wait a minute. Where's this? How do we factor with a GCF? Well, we're going to have to use a GCF here However, it's going to be more than just the coefficient. It's also going to be a variable, right? And we're looking here. Well, let's do one thing at a time. What's the GCF of 2, 8, and 6? That's right, it's 2. Very nice. So it is 2. However, we can go a little bit more big time with this because we have an x to the third, an x to the second, and an x. So we know that all three terms have at least one x in them, one x. So if they all share a common x, we can take that x out. Remember, when you're using the GCF method for variables, it's the minimum number of x's they all share, right? We can't take 3 out because even though this one has 3, this one only has 2, and this one only has 1. We can't take 2 out because that would work here because this has 3, this has 2, but this only has 1. So we can't leave this guy into a situation where we can't take the x out. That wouldn't really help us, right? So we got to make sure that they all have something we can remove, and they all have an x. So when we do that, it's division, and when we divide with exponents, we know that this is x to the first, even though we don't write that, it's understood. So 3 minus 1 is 2. And the 2's here cancel when you divide, right? So you have an imaginary 1 here, you know that. 8 divided by 2 is 4. And x to the second minus x to the first is just x. And then the x's here are going to cancel, and 6 divided by 2 is 3. Okay? Then you do a factor and sum, where you're factoring 3, and you're summing to 4. 3 is a prime number. The only factors of a prime number are itself and 1. That's a 1. It's a 1. Right? 3 times 1 is 3. 3 plus 1 is 4. And we know that x squared is factored in x times x. And then you solve for the root. Okay. So I think we've addressed everything we need to address today. Okay? And this will take care of everything you need to know about. Again, I'm going to do a Zoom video chat later. You're welcome to join if you have questions. If you don't have questions, you got other things going on, I understand. I put the times in Google Classroom. So if you're looking at Google Classroom, which you should be doing, you'll have all the information. I will send the link out later, so you have an understanding of what time and all that, and trying to think of other stuff. Charlie. Where's Charlie? Charlie, come on out and say hello to the people. You have anything? Come here, quickly, because we don't have a lot of time. They're busy, kids. Do you have anything to say to the kids? Charlie's in first grade. She's also doing online learning. So that's going pretty well. I hope it's going as well for you guys. We're here to help. And do you have any last words you want to say to the kids? No, nothing. Okay. She's going to be playing piano later, so tune in for that. I'll talk to you guys. See ya.